Good evening and welcome to Everything Matters, Tales from the Periodic Table. Tonight is, you'll never guess what? Beryllium. I knew you wouldn't be able to guess it, that's why I told you. Yes, this is the fourth month we've been doing this, so we've done hydrogen, helium, lithium, and tonight, beryllium, fourth element. I hope you all have your collector card, your lithium collector card. We hope you do, because it's a collector's item, and I hope, let's take a little poll. How many people have hydrogen? Good. How many people have helium? Oh, lithium? And you all have beryllium. Yeah, all right. Okay, collect them all. This is kind of like Pokemon. So next month, we are actually going to be taking a break. So next month, actually, if you look at the periodic table, between beryllium and the next element, there's a big gap. And so we're going to take that next month, and we're going to use that gap. And the month after, we're going to be doing boron. So don't think that boron is boring. It's boron. And so we're going to have some really cool things to do with boron as well. So we hope you would join us, and that's going to be on May 21st. So I'm your host, Ron Hipschman, and tonight we're going to talk a little bit about beryllium. It's kind of a really interesting element, and I hope you're going to enjoy it. We're going to have a guest after I talk a little bit about the physical and chemical properties and the atomic properties of beryllium. We have a guest, Jay Daniel from Tinsley Optical, and they are the folks that have been grinding the mirrors for the James Webb Space Telescope, and I'm not going to tell you why he's going to talk to us, but you might have something it has something to do with our topic tonight. We also, well, let's just start in, I think. I think it'll be interesting tonight because this is a very interesting element. Beryllium, as I mentioned, is element number 4. So you see the top two, hydrogen and helium. Then lithium is in the second row, and beryllium is right next to it. Beryllium is element number 4. It's atomic number 4. That means it has in its nucleus 4 protons. Let's just magnify that guy a little bit there. There he comes. Beryllium. It's atomic number 4, and you can see it's kind of a silvery metal, if you actually see it. Actually, we have some samples here that you'll be able to take a look at. And it has, we've looked at the sizes of some of these atoms in the past, and this atom is a little bit bigger than the ones we've been looking at so far. So there's a hydrogen atom on the left in the size of a beryllium atom, about 4 times as big on the right. About 1 angstrom. Anybody remember angstrom units from school? 10 to the minus 10th meters. Oh my God, that's really small though. So it's a very, very small atom. Some of the things that make beryllium actually really unique, one of the things I really like about it is its density. The density of beryllium is 1.85 grams per cubic centimeter. Now that doesn't mean anything to anybody I know. Water has a density of 1 gram per cubic centimeter, which means it's just not quite twice as dense as water. So if you actually had a lump of beryllium in your hand, it would be very light. As a matter of fact, I have a lump of beryllium right here that maybe we can get a shot of this on the camera here so that people on the web will be able to see it. You can see that this is kind of a crystalline composite here. And I want to pass this around so you get a chance to feel how light this is, how there's no word for not dense, how not dense this is. So let me just pass that around. I'll start it over here. So just give it a heft and feel how unhefty it is. We're missing some words in the English language here. So really, really light stuff. As a matter of fact, this is a cube, a solid cube of beryllium right here. And you may think that this is should weigh a lot. But actually, this cube of beryllium only weighs about 12.5 pounds. Now, if you had a cube of iron the same size, and for some reason, I don't know why, that the Exploratorium shop would not cast me a cube of iron this size. So, you can only ask. But I did fill a tub here with enough iron, so this tub would weigh as much as an iron cube this size right here. Would anybody like to try and lift this? Want to come up and try and lift this? I just want to get your impression here. First, lift this cube. Feel the beryllium cube. It's pretty light for chunk of metal that size. Now this is what the same size chunk of iron would weigh. Heavier or lighter?
It's a lot heavier.
A lot heavier. It's a matter of really hard. He made it look easy. I shouldn't have chosen some guy that was so buff. Okay, yeah. So it's actually really heavy to lift. I have a really hard time even getting that off the foam pad there. So really, really light beryllium. And that makes it very, very useful for some of the applications that we'll be talking about. We've talked about isotopes in the past. Beryllium has four protons in the nucleus, and this beryllium here has 5 neutrons. So that is called beryllium-9, because there's 9 total particles in the nucleus, and it's the isotope. As it turns out, how many stable isotopes of beryllium are there? Just one. That's it. This is it. There's only one form of stable beryllium. If you add a neutron or take a neutron away from the nucleus, it becomes radioactive. So this is unusual. We saw hydrogen had hydrogen and deuterium, 2 different stable isotopes. Helium had a couple of stable isotopes, helium-3 and helium-4, and lithium had a couple of stable isotopes as well. Beryllium has only one, so it's actually called monoisotopic. It's very rare. There's not many elements that are monoisotopic and only have one stable isotope. There are unstable isotopes of beryllium as well, and here you can see them. These are all radioactive. If you take an electron away from it, I can't even read my own slides here, it's beryllium-8, and that doesn't last very long. It's radioactive, and it has a half-life. That means that if I had a lump of it, half of it would decay in this time, which is 6.7 times 10 to the minus 17th seconds. So put a decimal point, 17 zeros, it's very short. It's 67 attoseconds. Go look it up. Go look up the bigger table in the metric system. It's a very, very small number, very quick to decay. There's even quicker ones to decay. Beryllium-6 decays in 5. Are you ready for this? Here's another great unit, zeptoseconds. Yeah, that's 5 times 10 to the minus 21 seconds. That's really quick. And there are other various ones. There's a couple of sort of stable, but they're radioactive, but they have a long half-life. Beryllium-10 has a 1.3 million, 1.4 million year half-life. And then beryllium-12 is beryllium-7 is 53 days. So there are some longer lasting beryllium isotopes, but 9 is the only one that's not radioactive, beryllium-9. Beryllium-8 is kind of an important one. Beryllium-8, which has 4 protons, 4 neutrons in the nucleus. It has a very short half-life. You see it's only 67 attoseconds, very short. But we are here, sitting here in this theater, because of beryllium-8. I know you may have a hard time believing that. In the inside of stars, you get nucleosynthesis. Atoms, nuclei are colliding with each other, creating new atoms. So hydrogen is turning into helium in the middle of our sun. Well, if you collide a couple of helium nuclei, what's a helium nucleus? 2 protons, 2 neutrons. If you collide 2 of those together, you get beryllium-8, which most of the time decays before anything else can happen to it. However, if another helium nucleus can collide with the beryllium-8, you can make carbon-12, and that's kind of what we're made out of, carbon-12. And so in stars, very old stars, I'll explain that in just a moment, you can get synthesis of helium burning in the middle of a helium burning star into carbon. Now it has to be a helium burning star because this has to happen at a high rate. If it's mostly a hydrogen burning star and there's a little bit of helium, but you make a beryllium-8 nucleus and it decays before it encounters another helium nucleus. If it's burning helium, an old star that's burning its ashes, essentially, if you can build up enough helium in the nucleus, in the center of the star, you can actually have this reaction take place often enough that this becomes an occurrence that happens before the beryllium-8 decays. It has to happen fast enough so that it happens before the beryllium-8 kind of explodes by a radioactive decay. So in a helium-burning star, you burn helium into beryllium, and beryllium you burn with another helium nucleus into carbon-12, and then that carbon gets redistributed into the interstellar medium and becomes us, carbon-based life form. So So that's actually pretty interesting. Another interesting thing about beryllium is it's very rigid. Sound travels through it very fast. The more rigid a substance is, the faster that sound will travel. And beryllium is right up there, man. It's like super rigid. And so if you look at things like air, sound travels through air at about 340 meters per second. 340 meters per second. But you look down there, aluminum, much faster. Aluminum's stiffer than air, so it travels 3,000 meters per second in air. But look at beryllium, the next one down. It travels at 12,000 meters per second through beryllium. Very, very fast. It travels about the same speed through diamond. And diamond's pretty rigid. So beryllium has an unusual aspect that sound travels very, very quickly through it. It's a rigid substance. Beryllium is not the cheapest stuff around. You're not going to find it in shops just laying on the shelf. It is a little expensive. Here's a chart of the beryllium prices over the years. Beryllium is now about $400 a pound. So it's moderately expensive. It's nothing like gold or anything like that, but it's fairly expensive. So if you want a cube of beryllium this size, it's going to cost you a little bit. By the way, these samples that you're playing with right now were provided by my good friend Ethan, who's sitting somewhere in the audience. There he is. He's sitting in the audience. He's an element collector. We all have our thing. And I used to have this thing too. I collected elements when I was in high school, and Ethan just sort of took it to an extreme and has the most amazing element collection. So he's actually been supplying us with some of these beautiful samples that you've seen. So where do you get beryllium from? Well, you get beryllium from a mineral, and this mineral is called, yes, beryl. You'll never guess why it's called beryllium. This was first synthesized, well, actually it was first kind of isolated as a different kind of earth. This guy didn't actually make the metal, but he isolated the oxide from the mineral in about 1798. So this fellow, and he called it an earth. Other folks had taken beryl apart, emeralds really, apart, and thought they were only aluminum and silicon and oxygen, aluminum silicate. This fellow found a little additional stuff left over. So he was the one he's the guy who's credited sort of with the discovery of beryllium, even though he didn't actually make the metal itself. The editors of the journal that he submitted his article to actually gave the name glucine to this new salt that he found because it tasted sweet. Something do not lick the sample of beryllium. You don't want to lick it. Beryllium has a mild toxicity to it, so we do not want to do that. A lot of these old chemists died from their discovery. We do not want to repeat those experiments. Another fellow gave it a different name. He called it beryllia because he thought glucine was also a name given to a different salt that was similar to the beryllium salt, but he didn't want to confuse the two, so he called this salt beryllia. This fellow here was the first guy that actually synthesized metallic beryllium, and he did it by taking the chloride of, should I put the chemical formula up? Why not? He did it by taking the chloride of beryllium, mixing it with hot potassium metal. Potassium is an element we'll get to, and what he got out was potassium chloride and metallic beryllium. So he was the first guy to actually make metallic beryllium. So what's it used for? It's used in a lot of things. I have here a gyroscope. Now, this is an old-fashioned, I don't know if I can unlock this. Let's see. This is an old-fashioned gyroscope that's used in airplanes, in aircraft. This has a fairly heavy steel cylinder that rotates very fast inside here, and if this was spinning, it would stay in the same orientation. You can go look at the gyroscope exhibit in our spinning things section back in, I don't even know what gallery it's in. It's just to the east of the West Gallery. That doesn't make any sense, but you'll find it. We have a gyroscope that you can play with. Nowadays, they use a different kind of gyroscope that looks sort of like this. It has a beryllium sphere on the inside that they spin electrostatically. And this beryllium sphere can can spin in any direction too, and so you can measure the roll, pitch, and yaw of your airplane or your spacecraft or your missile using a beryllium sphere. And that's one of the very, very smoothest things that's ever been manufactured, by the way, these beryllium spheres. Not the beryllium sphere you remember from the movie Galaxy Quest, which was a totally different thing. So beryllium is also used in X-rays. Beryllium is very, very transparent to X-rays. So this is just an X-ray tube, what an X-ray tube looks like. In an X-ray tube, they take an electron beam and they smash it into a target. And when the electrons stop real quickly, oops, sorry. There we go. When the electrons stop really quickly, they give off a radiation called Bremsstrahlung, braking radiation, and that exits the side of that tube right there. You can see the tungsten target has a copper heat sink. They have to cool that often with water because it gets very hot from this electron beam. And but that beam of X-rays, normally this tube has to be housed, and they house it inside something that has windows in it, and these windows are made out of beryllium because beryllium is almost completely transparent to X-rays. So that's an interesting use of beryllium, X-ray windows. Also, when you alloy beryllium, you can make interesting new metals. Copper, for instance. Copper is a very soft metal. It's malleable. You can damage it really easily. You can dent it really easily. But if you alloy it with a little bit of beryllium and bake it, you get a very tough alloy that's called beryllium-copper, and there are actually wrenches made out of beryllium-copper, and you would wonder, why would I bother with a beryllium-copper wrench when I could buy a nice steel one? But if you were a worker on a gas rig, an oil drilling rig, and you needed a wrench, you would want a wrench that when you hit something else that was made out of steel did not produce any sparks. That's bad. And so beryllium-copper wrenches are used where you have a gas valve or something like that, where you don't want to create a spark that might create an explosion. And so you can actually go on eBay and even Amazon and find these beryllium-copper wrenches. The oxide of beryllium is actually very useful industrially as well. It's a very good insulator, but it also conducts heat really, really well. So here's a beryllium oxide insulator that is used to feed a high electric current into a vacuum system. And there's another place where beryllium oxide is used that I'm familiar with, that I used to use, and that was in lasers. In very high power ion lasers, the tube that contains the plasma it gets very, very hot. You're putting a very large current through a plasma, an ionized gas, and that heats. You can't have a glass tube. It would heat the tube up and melt it. So you make on the side here, on the left-hand side, a tube made out of beryllium oxide. Not only is it resistant to melting, it's a ceramic, but it also conducts the heat out of the plasma channel, where you actually you have a water jacket that you take the heat away with a continuous flow of water. The lasers that I used to use were ion lasers that used actually this tube right here, and you had to flow 3 gallons of water a minute through these things. So I guess it's a good thing that we're not doing laser light shows now, because that used a lot of water, although we used to circulate it back. So that's okay. So I'm going to talk a little bit now about the gem qualities of beryllium. If you take beryllium and you combine it with aluminum and, like quartz, you get beryllium aluminum silicate. And this is a mineral that's called beryl, which is where the original beryllium took its name from. Here's what a beryl crystal looks like, and actually this crystal you can come up after, and the crystal is right here in the display case. Beryl, green beryl, well, there's some white beryl, most of that's white beryl, but notice there's a green beryl crystal there, and a green beryl crystal has a little bit of chromium that gives it that color, and that green color is the color of emerald, and indeed green beryl is what we call emeralds. So this is what it looks like in its natural state, and then you can see the one on the very right. Actually, I have a slide of it too, so we can go to my slides eventually there. Green beryl is emerald. The yellow one in the middle is called golden beryl. It's not an emerald. And then the bluish one is called Aquamarine. So those are all three different versions of Beryl, of the minerals that you see on the rock right there. Beautiful, beautiful. I kind of like the natural crystal myself. I would rather have the natural crystal than any of the gemstones myself, personally. But again, I'm a geek, what can I say? Okay, let's go back to the slideshow here. Of course, emeralds became known for, well, in movies we know of them where? You remember one place that you saw them in the movies? Of course, in The Wizard of Oz, the city was made out of emeralds. And actually, some people speculate that the Emerald City was just a metaphor for money, green cash, and that the yellow brick road, the gold road, and by the way, Dorothy originally wore silver slippers, was just an allegory to making silver a standard that you could spend money on as well. But so some people think this was actually might have something to do with a finance. But anyway, here's another Colombian emerald, another beryl, piece of beryl. And here's that emerald in the display case down here, just so you can see it a little bit larger. Again, the green color of the emerald is due to chromium. And we'll get to chromium at a later talk, but chromium is responsible also for the red color of rubies, but it's a different matrix that it's inside of. The largest emerald, well, there's a little bit of argument about that, by the way. Here's one contestant. Yeah, that's a pretty big emerald. That's called Theodora, that emerald. It's a 57,000 carat emerald that was found in Brazil. It was cut in India. It's about the size of a watermelon, as you can see. But there's a little bit of arguing going on here because it's believed that this is actually a white beryl that was dyed green. So there are methods that you can use to dye stones. And so there's a little bit of argument going on here. The gemologists are saying there might be actually some green emerald in there, but you can't tell because it's now being masked by the dyed part of the white beryl. This is actually the largest one that is probably legitimate. This is called the Bahia emerald. It weighs 840 pounds or 180,000 carats, and you know it hasn't been cut. You can see the beryl crystals there sticking out of the matrix. It's actually, again, I love this. This is just beautiful, I think. This one has such an interesting history, and I can't memorize this. I'm just going to read you the history here of the Bahia emerald. It's worth maybe $340 million, they think. This was carried out of a mine in the Brazilian rainforest more than a decade ago by a team of pack mules, one of which was killed by black panthers, and the cat. It was taken to the U.S. and stored in a warehouse in New Orleans. What happened in New Orleans? Well, that warehouse was flooded by Hurricane Katrina in 2005. It was then stolen from another warehouse in Los Angeles. The gem was then said to have been involved in a transaction involving a notorious Colombian family that nearly resulted in a bloodbath in the Nevada desert. It was also reportedly involved in a $197 million banking transaction with Bernie Madoff, who was then led away by federal agents 2 days before the transaction was to be completed in 2008. The emerald was next sighted briefly in Idaho before the authorities seized it in Las Vegas. The Los Angeles County Sheriff's Department currently has it under lock and key. So as you can see, this has had a wonderful history, this emerald, and it's probably worth more because of that wonderful story that goes with it. So that's kind of probably the biggest emerald in the world. One of the other stones that we have in the case here is the golden beryl. This is a really beautiful stone, I think. And this one is yellow because of an slight impurity of iron. Now, depending on what kind of iron you have inside there, you can also color a gem blue. And when it's blue, we call it aquamarine. So this is also an impurity of iron, but they're all a form of beryl. So there's one other form of beryllium crystal that's actually quite kind of nice, and it's called Chrysoberyl. It's instead of being beryllium aluminum silicate, this is beryllium aluminum oxide. And here's a natural crystal of Chrysoberyl. Really beautiful, looks like a snowflake almost. And Chrysoberyl actually is cut into a very interesting gem called Alexandrite, It's also used in lasers, by the way. Alexandrite changes the way it looks depending on what the lighting is on it. You can take it inside and it might look red under incandescent lights, but if you go outside in the sunlight, it'll turn greenish blue. So actually a really interesting gem.